Hello everyone. In the last video, we looked at what are binary heaps and how they are represented as an array in a program. In this video, we are going to take a look at how insertion and deletion of nodes work in a heap. Since binary heaps are represented as arrays, the first operation for any value would be to append it at the end of the array. Now let's look at the tree representation of this heap. As you can see that this is a max heap. So we would need to maintain the property that P should be greater than equal to C for any parent P and any of its child C. So for the newly inserted node, we will compare it with its parent element. This would be the second operation, which also takes O of 1 time. For the max heap, if the newly added element n is less than or equal to its parent P, then we would do nothing and stop. While if the newly added element n is greater than its parent, then in order to maintain the property of the max heap, we'd have to swap the two elements. This will be the third operation. This will also take O of 1 time. Here, since 50 is greater than 35, we need to swap these two elements. We'll have to swap them in the array as well. Now should we stop here? As you can clearly see that we are not following the max heap property for this element because 50 is also greater than 40. Hence, we should not stop here. Now we'll have to swap these two elements as well, as 50 is greater than 40. We'll have to swap in the array as well. So in the worst case, we'd have to repeat the step 2 and 3 for the whole path from the leaf to the root. What is the worst case in this case? It's when the newly added element is the maximum element. Or we can say that if the newly added element is greater than the root, that will be the worst case for max heap. Again, in that case, we'll have to repeat the step 2 and step 3 for the whole path from the leaf to the root. Now, how many operations would that take? Since both 2 and 3 are O of 1 operations in the worst case, we can say that it would be equal to the number of comparisons that we need to make so that in the end we get our max heap. Now that would be equal to the number of nodes from the root to the leaf. Isn't that the height of the tree? And what is the height of the complete binary tree having n nodes? It is log n. So we can say that insertion operations in a max heap or a binary heap would take order of log n time. Note that this would be same in case of min heap as well, as the number of comparisons that we need to make would be similar, but the actual comparison would differ, where we'd have to swap the elements only when the newly added node n is less than the parent. Again, for inserting an element in a binary heap, we first need to append it at the end of the array. Then we compare the element with its parent. Then we swap the parent and child based on our condition. And we repeat 2 and 3 until the property of our heap is satisfied. And it takes O of log n time to complete these operations. Now let's look at one more example for insertion. As you can see, this is a min heap. So the element at the root has the least value, and we need to follow the property that P is less than or equal to C for any parent P and any of its child C. So given this heap, if we want to add an element 8 in this heap, how will we do it? Well, first we need to append it to the end of the array. In this heap, what will be the end? This is the end element in this heap. We need to add 8 such that it comes after 35. We cannot add it here. So what will be the next place that we can add it? Since this level is complete, we need to start a new level. And since binary heaps are complete binary trees, we need to start the new level from left to right. So we'll append the child or append the new node here. Now let's compare 8 with 20. Since 8 is less than 20, this is not following the property of a min heap. Hence, we need to swap these two elements. Now let's compare 8 with 10. Since 8 is also less than 10, these two elements also do not follow the property of a min heap. Hence, we need to swap these two elements as well. Now let's compare 8 with 5. Now 8 will be greater than 5. Hence, this node follows the property of a min heap. Hence, we do not have to swap anymore and we are done with the operations. This heap that we have got follows the property of a min heap through and through. Now that we have discussed insertion, let's look at how deletion works for binary heaps. We mostly use heaps for getting the extremes, that is the maximum or the minimum at every step of the way. So we usually delete the top element from the heap. But the steps that we are going to take here would apply for any element. Let's look at how we can delete the top element from the heap. Since heaps are implemented as arrays, if we directly delete the root element, it would leave an empty space, and leaving an empty space in an array would complicate indexing and traversal. So what we can actually do is, if we want to remove the first element, we can swap it with the last element as the first step. This would take O of one time. Then, as the second step, we will remove the last element. This will also take O of one time. Now since the first element does not follow the heap property of min heap here, we'd have to replace it with any of the child so that the heap property is followed. But what child to replace it with? Since this is a min heap, it should follow the property that P should be less than or equal to C for any parent P and any of its child C. So if we replace 15 here, 15 will be less than 35. This will be correct, but 15 would be greater than 10. This will be incorrect. But how do we generalize it? In the case of min heap, when we are going downwards, we need to replace it with a node that has the least value. Hence, we replaced 35 with 10 and 10 with 35. This will be our third step, and this will also take O of one time. If you have understood until this point, try to answer this question. What child would we swap the parent with when we are using a max heap? Leave the answer in the comments below. Again, we repeat the process until every parent follows this property. That is, P less than or equal to C. Now in the case of 35 again, we can see that 35 is greater than 25 and it is greater than 20 as well. So we need to swap it, and we swap it with the least child, which in this case is 20. So we swap 35 with 20. Now if you check the heap, we'll see that every node will follow the property that P is less than or equal to C for any parent P and any of its child C. Hence we don't need to go any further. So again, for deletion, we swap the root with the last element. This takes O of one time. We remove the last element. This also takes O of one time. And we swap with the least child starting from the root until our element is at the right place and no more swaps are needed. So in the worst case, the third operation will take the total number of comparisons that is equal to the height of the tree, which will be O of log n. Hence, we can say that deletion also takes O of log n time in a binary heap, because at every step we are going to swap with the least child until our element reaches the right place where no swaps are needed. Now let's quickly look at another example for deletion. This is a max heap. Let's delete the node 50. For that, the first step would be to replace it with the last element. Now in the second step, we need to delete the 50 from our tree. Let's delete it, and let's just update the last pointer to point at an element which is before the last element. So we'll push this pointer here. Now the last element of our heap is 35, and in the third step we need to bubble this 10 downwards. So we'll replace it with the maximum child so that we follow the max heap property. Again, we see that at node 10 the max heap property is not being followed. we'll have to bubble it down again. Since it has only one child, we'll replace it with that child, and hence we are complete with our first deletion. And we can see that the max heap property is being followed at every node, be it 40, 35 or 10. Now let's say, for the sake of this example, we had to delete all the elements from the heap one by one. So in the next turn, let's delete 40. Again, in the first step, we'll have to replace it with the last element, that is 10. Again, let's update the pointer. Instead of deleting the whole element from the array, so this pointer goes here, and let's remove the last element from the tree. Now the last element is 25. In the next step, we need to trickle down or bubble down the 10. We'll replace it with the largest child so that the max heap property is followed. Now we can notice that the max heap property is being followed by every node in the heap. So we can move on. Now let's try to delete 35. For that, we'll first replace 35 with the last element in the heap. Again, we'll move the pointer to the element before the last element. So this pointer goes here. Then we need to bubble down this 25. We'll replace it with the largest element so that the max heap property is being followed. Now, if you notice that the max heap property is being followed in every node of the heap, let's move on to the next iteration. We now need to delete 30 from the heap. We'll first replace it with the last element in the heap. Now we again update the pointer and delete the last element from the heap. Now we need to bubble the 20 down. We'll replace it with the max element so that the max heap property is being followed. Now we can see that for every node, the max heap property is being followed. Let's move on and try to delete 25. In order to delete 25, we need to replace it with the last element in the heap, which is 10. Now we update the pointer again and delete the last element from the heap. Now we need to bubble down 10 so that the max heap property is being followed. Now the max heap property is being followed, so we can move on and try to delete 20. For deleting 20, we need to first replace it with the last element, which is 10. Then we update the pointer so that it points to the element before the last element, and we delete the last element from the heap. Now, since we have only one node remaining, this will follow the max heap property no matter what. So let's try deleting this node. When we delete this node, we just can remove it and update the pointer so that it points to -1, which is not possible for any array, so the loop stops. Now, if you look at this array, this whole array is sorted, and the procedure that we followed is called heap sort, where we deleted the first element from the heap and preserved the deleted element, and we saw that the deleted elements were in sorted order. So this is heap sort. Thanks for watching. If you learned something, please like this video and subscribe to keep learning.